in the room here today, what we do is we solve problems, and when we have a problem to solve, we sometimes will build a custom electronic system, and we will use off-the-shelf parts, and we heard Tim talk about that just before lunch, for example, from Microchip. But sometimes those chips aren't good enough, and so it's time for a custom chip. So that's what CMC is about. So I just want to talk about that today. So we're a national organization, as I mentioned before, and what we do is we help researchers across Canada, institutions and colleges, including here at l'INALGRU, to design microchips, to manufacture microchips. We send those out for manufacturing, to test the microchips, and to partner with companies around the world on their projects. That's not what I wanted. So some of you may be familiar with some of the tools that are used. So basically, if you have an idea, Claude is on my right here, has done this through CMC. So Claude Thibault from ETS. So if you have an idea, you can use some of the software that CMC makes available. You can design your chip, and then you can send the data to us. And then magically, 3 or 4 months later, we will send you your own chip. And you get maybe five samples, 10 samples. You can test those and then move on. So it's useful for research and useful for university collaboration with companies and college collaboration with the companies. I can tell you, when you design your own chip, it's a whole different world. The NRE could be 10x, it could be 100x, but the payback can be there, right? So companies do it for a variety of reasons, obviously. We use chips every day, but if you design your own chip, you can really embed your own IP in that. You can protect it that way. You can build some very novel structures. And one of the things that we're doing is, as an organization that CMC is doing, get more and more involved at the materials level. So I'll talk about that. So just a little bit on the National Design Network. There's about 5,000 students and faculty that use our products and services. About 1,000 faculty are connected with CMC, and you can see some of the numbers here. And the way, as a not-for-profit, that we measure our success is through the number of publications, international awards, startup companies, investments of in-kind and cash into projects, and so on. We access a global supply chain for chip manufacturing, and so typically, quite often, the chips are manufactured at TSMC, one of the world-leading foundries in Taiwan. So indeed, if a student here at l'INALGRU sends us the data, we will send them back chips that will have been manufactured in technologies with feature sizes as small as 28 nanometers today, and getting more and more small. So this is just a snapshot. Make sure it's the right slide. Yes, it is. Just a snapshot of the types of companies that the faculty who work with us work with. So I mentioned there's about 1,000 faculty, 650 of them are paying subscribers, and they collaborate with the companies. If you can, it's hard to see the slides in this room, but if you can look down the far left edge of that, it says microelectronics, embedded systems, materials engineering, integration, and so on, and photonics carries through there. So the faculty across Canada are working with a very wide variety of researchers, and you may identify yourself as one of those, perhaps, but you're not using the CMC supported infrastructure. So give us a call. So this is a breakdown of the pie charts here, and for those who can't read it, on the left is a technology application, and basically you're looking at the a reasonably wide distribution of entertainment, ICT, defense, aerospace, and so on. The design-oriented interests going all the way around there: analog, mixed signal, embedded systems, microfluidics, photonics, and so on. And then the disciplines and departments. What's obvious on that one is half of the pie chart is electrical and computer engineering, traditionally in the VLSI microelectronics world. However, that portion of the pie is going bigger and bigger. We have about an 8% compound annual growth rate in users of CMC services, but the proportion of electrical and computer engineering is slowly shrinking over time as the microchips become more and more useful to people who might be in engineering physics, working on a deep space exploratory telescope, or they're in mechanical engineering and they're working on a prosthetic arm, or et cetera, et cetera. Chemistry, chemical engineering. So a little bit on the technology. This is a diagram that you probably can't see from where you are, but this is what it's obviously a work in progress because of the annotation you see on there, but we call this the technology space of the National Design Network. And at the top are areas that we see as drivers: information communications technology and advanced manufacturing, video and things, as in Internet of Things, virtual reality, augmented reality, and system control. are very hot drivers. And then as you head down into the chart, you get into kind of the realm of what we see as significant. This is a slide that went to one of our technical advisory committee meetings where we bring together experts 2 or 3 times a year to talk about the futures and the roadmaps. So heterogeneous computing, this is a business of using alternative fabrics, FPGA, GPU, Xeon Phi processors, and then a host computer, maybe some other novel fabrics, bringing those together, making use of those in applications such as AI. 5G is very hot if you're into the business of trying to secure some funding in Canada right now. It seems to be a very hot topic, data centers, sensing and actuating. So those are, again, drivers. Where we get involved is the development systems and then the chip manufacturing, and you can see that more described in the bottom here. So the packaging and integration, microelectronics, MEMS, and microfluidics with a question mark, and photonics, silicon photonics, and alternatives, 3.5 optics, and so on. So that's the middle of our world, and at the bottom there you see nanofabrication labs, materials, devices, and processes. There are 35, maybe 40 micro-nano fabrication labs across Canada, and they will make parts for you. They can't make parts like TSMC in Taiwan does. They don't make a 8-metal interconnect high stack with FinFETs or FDSOI devices buried in the substrate. But what they will do for you is some pretty interesting post-processing or material development. They may functionalize surfaces, change the sensitivity or selectivity of a sensor that you're working on, post-process a microelectronics chip, maybe to put, I don't know, if you've got a microelectronics RF chip and you want to try some kind of unique spiral inductor on top of the chip, they can build that for you. Maybe an on-chip antenna, that kind of stuff. So you have the chip made at CMC through the usual processes, and then you take it to a lab in Canada and have it post-processed as I just described. So again, why would you do that? 10 to 100 times the effort, but what we're doing is, we being this community I'm talking about, we're not designing solutions using yesterday's technology, we're designing tomorrow's technology that'll end up in the chips that people will be using to solve problems. So that's the technology space. Photonics was shown on that diagram, and this is a very busy slide that's been used in a number of places, but if you glance at these 2 charts here, the blue one is the number of designs we've manufactured starting in 2008, and the red one is the area, silicon chip area. It has been climbing like crazy. So photonics is very hot in this space. We have some large and small companies working with CMC making photonics devices. We have a lot of researchers making photonics devices, and the community is growing. So Canada's had expertise in long haul, fiber from city to city and so on, but certainly the photonics chip to chip on a board, or actually on the chip, and we're starting to see I've seen them, some silicon photonics devices coming into CMC for fabrication that are not just a waveguide. I don't know anything about photonics, by the way, but they're not just a waveguide, they are a circuit. They're not just devices, they are a circuit. The light comes in here and it goes through there and it gets modulated here, and then this happens, and then this happens, and then it comes out here and then it exits there, that kind of thing. So if you're interested in a subject, photonics might be one. This is some of the design environments we have. I can't even read that from here. But what I do want to say is that we are moving to a lot of the very expensive CAD tools, computer-aided design tools that would be necessary to do chip design. We're moving those into the cloud. And so as a CMC user, you can fire up the tools and display them back. And yeah, there's a little bit of delay with the mouse and so on and so forth. But zero install, sysadmin effort near zero, right, et cetera. Access to PDKs, yes. So something to think about for your research. I spoke about heterogeneous computing systems. So this is a diagram of one of the ones we sent out. But the message I want to share here in terms of the future of electronics is a heck of a lot of interest in heterogeneous or different fabrics for doing computation. As you know, clocks stopped at around 2 gigahertz on chips from Intel and so on, and now we just can put more into a core or more on a board. But can we start using some alternative fabrics? And so the business of using an FPGA plus GPU plus specialized CPU plus host CPU in an accelerator form, or maybe symmetrically and to solve problems, that's one challenge, getting that all talking to each other. The other challenge is to make it so that the programming environment is usable by let's call it a Compute Canada type of user, where I'm modeling the air over a wing. I don't really want to know about RTL, timing closure, and all that kind of stuff for using an FPGA, but I do want to use them because they're really, really fast. So that whole problem is a really neat engineering problem that once we solve it, it won't be of interest to us anymore because now the users get to use it. We'll move on to something else, maybe related to quantum computing. But that's a very hot topic right now, especially the usability of it. So you might wonder why Intel bought one of the two largest FPGA companies in the world, which was Altera, a year and a half ago or so, and that's your hint. So just a few more slides here. So again, in Canada, there are 35, maybe 40 micro-nano fabrication facilities. There's quite a few here in Montreal, McGill and Polytechnique Montreal and so on. And we're involved in a project here with Lionel Groux, and Polytechnique will be putting in some capability if it's funded. These labs are there. They're doing what they want to do, but they're always interested in more business. Or they're interested in developing their labs, interested in collaborating and cooperating in some cases, and perhaps even generating some revenue from operating to help pay for their operating costs. And so what we're doing is we're trying to help those labs glue it together. And so we now have services available to access these labs. And just a few slides on that. And by the way, I'm telling you this not because I want you to use products from CMC. That's up to you. We're not for profit. We're mission driven. But because I think that's part of the future of electronics. The leveraging of the manufacturing available in micro-nano fabs to harness great ideas in different ways other than the traditional microelectronics. We absolutely need that silicon. It's 90% of what's going on. But there's some really cool stuff you could do around sensors and actuators and MEMS and microfluidics and photonics and so on to generate value. So if you want to use a lab in Canada, we have Fabrication Assistance Awards, $2,000 for the access fees. So if you're a student here at Lionel Groux and you want to go to Polytechnique Montreal and use their lab, they'll say, well, it's $60 an hour or something. So you can apply to CMC and get support for that. And travel. If it turns out there's no lab here in Montreal area that can do the type of steps you want to do to your chip or to your specimen, then you can apply to CMC and we'll offset the travel costs for you to go to, I don't know, the quantum, the IQC at Waterloo, for example. What people don't realize is that, and I say this everywhere I go, and they go, wow, you can use these services to access the labs in your own institution. Okay, so if you're a professor at ETS or Poly Montreal and you want to use the lab at Poly Montreal, you can use these services to access the lab down the hall and offset the costs. So what we've done is we recognize that some of the labs want to escalate. They want to increase their capability to a level of service orientation. In other words, it's more than just a room of equipment. It's actually a room of equipment that's calibrated, serviced. You can book it. Maybe even comes with people. But maybe even a higher level than that, it's a room of equipment where there are some documented processes. Maybe there's some capabilities that they're known for, some particular material they work with, some processing steps they're known for. And they have a service orientation, and they want to not only help people do their research, build their prototypes, but maybe generate some operating revenue from those transactions. And so we have what we put together called the FACT network, Fabrication, Assembly, Characterization, and Test. And I think we're up to 5 labs in the FACT network. So these labs need, when a lab, we work with all the labs, when a lab starts to behave in a way that an external committee is determined to recognize them for this service level, then we will add them to the FACT network and have the system reward the labs that want to work that way. And so the FACT network is part of our services, and you can read about it on our website. Especially nice if you're working with a company that might want a prototype by a certain date, for example. So it's just an example of the types of stuff we do, right? So a laser milling and aerosol jet deposition, that's a $500,000 machine at UBC, and inkjet deposition machines and e-beam lithography machines. We put $1 million e-beam lithography machine over in the Bombardier building at Polytechnique Montreal, for example. So if you want to play with this toy, this is one way you can. This would be one way you can. So just a few slides on some of the types of projects we're working on, just a really small sample. We're working with a company called InnoTime Technologies, actually based out of here in Montreal, and they're working with University of Sherbrooke and other suppliers, and we're working on a interposer technology. So this is a piece of silicon, flip chip, some devices on it, or maybe just have them face up, chip on board, bond wires. In between these flip chips and the piece of silicon is 2 layers of redistribution layer interconnect that will be manufactured at University of Sherbrooke. The silicon has through silicon vias, and then on the bottom there's another redistribution layer and balls, BGA, ball grid array. So is it any technology like you'd see in those, Micron or Samsung memory companies where they stack 8 chips? No, of course it's not, but it's a technology accessible to faculty, researchers right here in Canada. It's actually a journey. We're working on it, and they're working on it. We're having our first fabrication run right now, making devices for a collection of lead users. So if the size of the prototype matters, for example, centimeter cubed, a printed circuit board is not a great thing to put at the end of an endoscope, but a centimeter-sized prototype, or maybe a controller for a prosthetic that just can't be like a PC on your back, where the size matters, where the integration degree matters, where maybe you want to reduce power for an IoT device, and the size really matters. And I know that's one of the applications they're working on. This will be an interesting technology to play with. So you supply the die, maybe you make them through CMC. You can get chip scale packages online all over the place, and then we'll find a way of packaging them. Could be fun. This is an example. This is Régent Fontaine, University of Sherbrooke. He's working on his PET scanner, and he needs modules, and we're helping him build those. Just another example of the type of thing. So here we had a client request for embossing mold for optical grading couplers and polymers. So this guy wants to couple, guy or woman, I'm not sure, wants to couple a fiber to a chip, I believe, and they needed some kind of coupler on the surface of the chip. And so we identified the labs that could make those steps, that process that chip to do that, E-beam etch, the mold replica, the embossing, and then manage the project. So we had the device made, and it led to some outcomes. So we have low volume delivery coming out of some work there. So that's an example of the kind of stuff we could do. And it leads to startup companies. It's just an example here. This is a company called Engage. I think it spun out at University of Waterloo. Dr. Rafat Mansour's lab there on MEMS. So here we have the world's smallest and simplest, most affordable atomic force microscope. So the tip is a MEMS device, all on a single chip with some support electronics. The whole thing's about this big, and it sells for $500. I can't remember what it sells for, 1,000, some number like that. But you can go online. And they raised some money, and they've sold a handful of those. And the last I talked to them, they had to deliver them in December. I haven't talked to them since. But this is with a lab at University of Waterloo where they did some micro-nano fabrication, some support from CMC, the use of our CAD tools, and some really smart engineering going on by the principals. So I think second last slide here, I just wanted to mention again, we're a not-for-profit organization here to support research across Canada in all corners of this of Canada, and we measure our success by I think the same way many of you do: number of trained students, number of publications, the funds raised for collaborative research, industrial sponsorship that's domestic, that's with international firms, et cetera. And those are some of the numbers we've gathered. So last slide is to say thank you, and I hope I didn't go too much over time, and to mention that our next annual symposium will be on, what is the date? September 25 and 26 in the beautiful city of Montreal, and we invite you to join us for that, to hear more about what's going on by your fellow researchers and some of the companies they work with. Thank you.